Hey there! Welcome back to the National Solar Observatory for the next installment of our Eclipse webcast. In previous webcasts, we've covered the layers of the atmosphere. We've talked about the layers that are going to be visible during the solar eclipse, specifically the chromosphere and the corona. We've also talked about how the sun is magnetic and how it has an inherent magnetic field that ends up being the source of a lot of its activity. So today we're going to delve a little bit more into that solar activity and just figure out the difference between solar flares and CMEs and prominences and filaments. We also have a very special guest, Dr. Alex Young from NASA's Goddard Space Flight Center, who's going to give us the scientist's perspective on space weather and on solar activity and why it is important for us that we study these phenomena in the first place. Okay, so let's get started. Space weather is a term that's becoming more and more popular every day. You may be hearing about it in the news, you might even be hearing about it coming from the government. And this is because it's something that's actually quite important to us, not only from a scientific perspective, but also from an everyday life perspective. Space weather is a phenomenon that's caused by the sun that can have an effect on things like GPS signals. So while it can have effect on our cell phones and on the reliability of your applications to get you from one place to another, it's also something of very significant interest to, say, the Department of Defense or to commercial airlines. So what exactly is space weather? So on the Earth, we have weather systems that affect our everyday life. We look at the weather channel to see if it's going to be raining today or if it's going to be sunny or if there's a hurricane forecast. And scientists can use mathematical models to predict what the likely weather is in a particular place on the Earth at any given time. Likewise on the sun, we try to use solar activity and things that we can see occurring on the sun to try and predict what the sun is going to do in the near future. We have a long way to go yet. We're nowhere near as close as Earth weather predictors are, but we're making progress. So last month we talked about the fact that the sun is magnetic. It has an inherent magnetic field that in its simplest form looks a little like a bar magnet, but is generally much more complex than that, with big loop structures that come out from its surface and magnetic field structures that start at the surface of the sun and actually reach all the way out into space. Scientists can study the changes in these magnetic behaviors to try and predict what the sun is going to do. So we have observations of what the sun has done in the past, and we use those observations to try and identify features or behaviors that the sun might have that will help us to predict that a solar flare or a coronal mass ejection might be coming. So it's very important to know that solar flares and coronal mass ejections happen all the time. They happen multiple times a day during the peak of solar activity, and even during solar minimum, they happen on a semi-regular basis. So they're not something that in general we need to be concerned about. Now, every few hundred years, we do get a monster solar storm that could potentially have quite a hazardous effect on Earth. One of the biggest concerns that we have is that it can induce electrical currents in our electricity grids on the ground that might completely blow electricity grids all over the world. This actually happened as recently as 1989, where the entire city of Quebec lost its electrical power as a result of a solar storm overwhelming its electricity grid. So the study of space weather began in 1859 with what's commonly known as the Carrington event. The Carrington event was a very, very large geomagnetic storm or solar eruption that hit the Earth, and it sent magnetometers, which are instruments for measuring magnetic fields on the Earth, off the charts. There was aurora seen almost as far south as the equator. There was aurora observed in Cuba, for example, which is unheard of. Normally the aurora is only seen close to the North and South poles. So this Carrington event storm really initiated the study of space weather and the fact that the sun, even though it's a celestial body and it's something that we depend on for our light and heat, can also have a negative effect on our everyday life. And it's something that we need to understand and need to appreciate and be prepared for in the event of a similarly large solar storm. So when we talk about space weather and solar activity, what exactly are we talking about? We've mentioned the word CME or coronal mass ejection, and we've mentioned the word solar flare. But what are they and how are they connected together? Are they the same thing? Are they dependent on each other? The easiest way to think about solar flares and coronal mass ejections, or CMEs for short, is that they're two sides to the same coin. So the way I like to think of it is like a hot air balloon rising from the surface of the Earth up into the atmosphere. So in this case, here's our hot air balloon, and our hot air balloon represents a blob of material that's suspended in the corona in what we call a coronal loop. And these loops are generally large. They're larger than the diameter of the Earth, and they're filled with hot million-degree gases that are trapped inside of these loops. So here we have our hot air balloon that represents our coronal loop, tethered to the sun using magnetic fields. So in this scenario, our magnetic fields are represented by the ropes that are holding our hot air balloon down onto the ground. What happens if our tethers get really wound up, or if there's a lot of stress put on them, so they start to fray and they start to snap? That's our solar flare. So a solar flare is a release of energy, and this is seen generally as a flash of light. So a solar flare doesn't ever really leave the sun. It's the sudden release of energy that results in a very quick and very powerful flash of light. Now, as our tethers begin to fray and they begin to snap, our hot air balloon begins to rise. And in this case, the hot air balloon represents our coronal mass ejection. So this is literally an ejection of coronal material. It also includes magnetic fields, but it's the stuff, it's the material that leaves the sun and propagates out through space. So now we have our hot air balloon that has been released by its tethers, that is rising up into the atmosphere, which represents our coronal mass ejection. And as you can see, our flare is over. The release of energy happens at the beginning, where the tethers are broken and they're frayed, and that's the solar flare. And then as our hot air balloon is rising away from the surface, and that's the coronal mass ejection, or the ejection of coronal material and magnetic field. And it's these coronal mass ejections, or CMEs, that become the geomagnetic storms. So they're called geomagnetic storms if they are approaching the Earth. So the Earth has a magnetic field of its own, and these CMEs are filled with magnetic field also. And so the interaction between the magnetic field in the coronal mass ejection and the magnetic field of the Earth is what causes the Earth's magnetic field to reform and to inject energy into the Earth's atmosphere. And this is actually what causes the aurora borealis and the aurora australis. So this is why we get aurora. It's as a result of geomagnetic storms interacting with the Earth's magnetic field, causing it to peel back and fold back on itself and inject energetic particles that travel along magnetic field lines to the North and the South Pole. And as those particles interact with the atmosphere, they get rid of their energy. Their energy has to go somewhere. And in this case, they deposit their energy in the atmosphere, in the atoms in our atmosphere. And so those atoms then start to glow to dissipate the energy. So different atoms at different heights in the atmosphere give off light of different colours. So we get beautiful reds and purples and greens moving like sheets in the upper atmosphere as the northern and southern lights. Okay, so let's go back to the sun, which is where we're going to try and keep our focus today. Today we're interested specifically in coronal mass ejections, because if we get really, really, really lucky during the solar eclipse, there may be a coronal mass ejection. I said earlier that scientists are working to try and predict space weather and solar activity, but it's really very difficult to do with any advance warning. So we've discussed the differences between solar flares and coronal mass ejections. And the other two terms that are very frequently thrown about are prominences and filaments. And during the solar eclipse, again, a prominence is something that it's very, very likely that you'll be able to see. So that first of all, the difference between prominences and filaments are none. They're exactly the same thing. So scientists observed prominences and observed filaments at different times, and they did not realize that they were actually the same phenomenon because they look very different. The only difference is that a prominence occurs on the limb of the sun, but if we see it on the disk of the sun, so looking at the face of the sun, then it's called a filament. They're generally blobs of cooler gases suspended in the atmosphere by magnetic fields. So because they're in the atmosphere and because they're cooler than the gases behind them from the surface, on the surface they appear dark. They're absorbing the light from the material behind them. However, when they're on the edge of the sun, or on the limb of the sun as we call it, there's no light from the material behind it to absorb, and so it appears bright. So that's the confusion between a prominence on the limb or a filament on the disk. Fingers crossed, on eclipse day there will be some prominences that we'll be able to see, especially once the sun is completely eclipsed by the moon. And even not on eclipse day, if you have the opportunity to look through a solar telescope, you will be able to see solar prominences off the edge of the limb of the sun. So to recap, today we've talked about coronal loops, which are large regions of hot gases suspended in the atmosphere. We've talked about filaments and prominences, which are the same thing, and they're large regions of cool gas suspended in the atmosphere. We've talked about solar flares, which are the sudden release of light and energy, and we've talked about coronal mass ejections, which is an eruption of material and magnetic field that flies through space. So in case you're worried about coronal mass ejections, it's worth remembering that coronal mass ejections are ejected in all directions away from the sun. So around the sun there's 360 degrees, and of those 360 degrees the Earth only takes up half a degree. So even when there is a large event, there's no guarantee that it will actually interact with the Earth. As always, if you would like to hear more from us, please feel free to get in touch. You can find us on Twitter at NatSolarObs. You can get us on Facebook at National Solar Observatory. And we now have an Instagram account at National Solar Observatory on Instagram.